Well, thanks very much for the opportunity to give this talk at this KITP reunion conference. I remember the main conference 3 years ago very well. It was a great chance to get together with collaborators such as Matt von Hippel, who gave a talk at the conference about similar work at the 6-point level, and Simone Carenhois and Andrew McLeod and others. And this work is done with a PhD student, Andy Liu. And you may notice, those of you who were at my talk at Amplitudes in May, a certain amount of similarity between the two talks. But there are a few differences throughout, which the alert audience member may notice. And the ones who aren't alert, well, they probably will benefit from seeing it a second time. So everybody, it's a win-win situation. So first of all, the title of the talk at Amplitudes didn't have through for loop NMHV. So we've been able to push to that order, which not only allows us to put more lines on some plots later, but it also gives us 15 times as many functions at weight 8 as we had when we had the MHV amplitude, and we can explore more of a certain heptagon function space using that data. And another important thing is that the paper is out now. So before, if you had questions about the talk that I couldn't answer, you had no recourse, but now you can read the paper. And also, I wanted to mention that this title involves lifting symbols to functions. As we'll see, a symbol is like a scaffold on an amplitude, sometimes referred to as a shadow of the function itself, but only when you put the meat on the bones or the flesh on the top do you get something sort of real, and we'll discuss that more as we go along. So the context for this calculation or result is in planar n equals 4 super Yang-Mills theory, which is a theory that many of us know and love. And when we take the gauge group SUNC for the maximally supersymmetric gauge theory and go into the large N limit, we find that the structure of the endpoint amplitudes is very rigid. I'm just going to shut off my phone for a second so Siri doesn't respond.
Yeah, sure. She can ask a question.
Yeah, maybe Siri could answer some of the questions you might have too.
I'll ask.
So in any case, in planar n equals 4, we know a huge amount about the amplitudes from the very beginning. We know that they decompose into rational times transcendental, summed over various structures. But more to the point, the number of rational structures is very limited in terms of certain dual superconformal invariants. And we understand them so well that I'm not going to say anything about them. I'm just going to focus on the transcendental part from now on. The space of these transcendental functions is also very restrictive in simple amplitudes, meaning 6 or 7 point amplitudes. And the physical constraints are so powerful, we can basically write down the answer as a linear combination of known iterated integrals called generalized or multiple polylogarithms. And at L loops, we just have to draw the answer from a space which has weight 2L. And if we think we know what the function space is, we just write down a linear combination with unknown rational coefficients, and we solve the linear equations by imposing boundary conditions in some data, for data in some limits. And if we have enough limits, we can determine these coefficients. And in fact, this is usually the easy part of the problem. The hard part of the problem is constructing the space. Finding the amplitudes in the space is a much easier problem typically. So this problem was first carried out for the first non-trivial function amplitude in planar n equals 4. The 4 and 5 point amplitudes are completely constrained by the symmetries of the system to have no non-trivial kinematic dependence. But the 6 point amplitude has that dependence, and we've been able to get to 7 loops. And you may also notice, if you were paying attention to my talk at Amplitudes, that I didn't specify the month that this paper would come out, and now I have. So you can see I'm very optimistic now, but then August has 31 days, so it's a long month and a lot could happen. Anyway, we've now gotten through the 7-loop order, and in published work, the MHV case, and coming up, the NMHV case. So, and we do all this without ever inspecting or harming any loop integrand, but just writing down what we expect the functions to be after integrating over all the loop momenta. The less we can inspect the loop integrand, the less reliance there is on the order in the loop expansion, the more chance we have of being able to do this sort of thing non-perturbatively for general kinematics. And we can poke at various limits where there is some non-perturbative information available and eventually try to meld it all into a finite coupling description of arbitrary scattering amplitudes. At least that's the dream. But so far at function level, this whole game for arbitrary kinematics was mostly limited to 6-point amplitudes. And the point of this talk is to tell you that we can now redo the same sort of thing at the 7-point level as well. So we'll be able to push to 4 loops. So this is the second in the 4-loop session of this conference. But in this case, the functions that we're going to deal with depend on 6 different kinematic variables. Whereas in the 6-point case, they only depend on 3 different kinematic variables. So it's a much bigger space to wander around in, and it's nice to have some lampposts so that you don't get lost. So I'll try to describe some of that. One important lamppost that has to do with the scaffolding is cluster algebras. And it was shown by Golden, Goncharov, Palos, Spradlin, Volovich, and Vergu, or suggested what the right space of polylogarithmic functions should be. And there was also more developments by Drummond, Foster, and Gertigan, and other papers by these authors and their collaborators. And using some of this information about what the right letters were, Drummond, Papathanasio, and Spradlin were able to bootstrap the symbol of the 3-loop MHV 7-point amplitude. And they found, remarkably, that it was sort of more rigid than the 6-point problem. Fewer constraints were needed. At the 6-point problem, even with understanding the function space very well, we still need to use the Multi-Regge limit as a constraint. That wasn't necessary here. Also, with the Steinman relations, one could restrict the space even further, and using the fact that the space of functions was more tame or more under control, one could go to the 4-loop MHV amplitude and the 3-loop non-MHV symbol, both at symbol level. That was work I did with James, Andrew, Thomas Harrington, Yorgos Papathanasio, and Mark Spradlin in 2016. And then in 2018, James, Omer Gertigan, and Yorgos applied the extended Steinman relations, which trims the space even further, and they were able to get to the 4-loop NMHV symbol. But as you can see, this was all work done at the symbol level, and you still need to go from the symbols to actual functions. So I want to give a little bit of motivation, but first let me give you a sort of heuristic view of what this function space looks like. And in general, it's a set of iterated integrals of special type, multiple polylogarithms. But basically, at each weight, the number of integrals is denoted here. So at weight 4, you'll have some kinds of 4-fold integrals. At lower weight, they tend to be classical polylogs of suitable arguments. In the 6-point case, the dialogues you find at weight 2 happen to have special arguments like this. And you also have log squareds of certain combinations of cross ratios. And interestingly enough, you have a 4 zeta 2 that sits in here. Now, these zeta 2s, these zeta values are totally invisible at the level of the symbol. And so one of the things you learn when you go from the symbol to the function is where are the zeta values. So it's all about attaching zeta values in the right way to the derivatives of functions. And here's a zeta 4 sitting off by its lonesome. For example, this is actually an independent zeta value that doesn't have to be attached to a different function. Whereas this zeta 2, in both the 6-point and the 7-point case, has to be attached to various logarithms or symbol level functions. So we'll get into that in more detail later. So why should we go from symbols to functions? Well, one motivation is that the LHC, which was some of the origin of all the motivation for doing this work in a different theory, QCD, it doesn't measure symbols. It measures functions. You have to evaluate things to numbers. It's not good enough to give the symbol. So we're not doing this for the LHC directly, but we want to illustrate that it is possible to compute these amplitudes completely numerically and make plots, which you can't do with the symbol. For example, at the 6-point level, we can make plots that involve the ratio of successive loop orders, in this case, in the NMHV case, through 7 loops, which should come out soon. But you can find MHV plots in this paper from over a year ago. And there's a lot of structure in these kinds of plots. And there's a indication of the finite radius of convergence in this region, which I'll come back to later in the 7-point case. But in the 7-point case, there were almost no plots available before our paper. In fact, the only plot I could find is one by John Golden and Mark Spradlin from 2014, where they plotted the 2-loop remainder function on a particular symmetric surface, which we'll come back to later. So although I said LHC doesn't measure symbols, of course, yesterday I had to go and Google on LHC and symbol, and I discovered that the LHC is actually a symbol. It is one of 60 symbols. And if you want to learn more, you can go to the University of Nottingham and try to figure out what all these symbols mean. But it's a public outreach effort. So there you go, the LHC is a symbol. Okay, here's the second motivation. And I'm sorry for recycling this joke from previously, but if you've read enough comic books or seen enough Marvel movies, you'll know that every superhero has an origin story, where they came from. And we believe that every super amplitude also needs an origin story, or some region where the amplitude simplifies and yet things become quite interesting. And so far, we have only one example of this in print, the hexagon case, n equals 6. When you take all 3 cross ratios in the hexagon to 0, something remarkable happens. The logarithm of the MHV amplitude becomes very simple. It is only quadratic in the logarithms of the cross ratios. In principle, since this has weight 2L, it could have weight 14 at 7 loops. But in fact, it's just quadratic. Now the whole answer has weight 14, so there's a weight 12 zeta value sitting in front of it at 7 loops. Well, this was all discovered in paper, actually this is probably the wrong paper, probably the March paper from 2019. Anyway, the zeta valued coefficients, these C of zetas here, in work in January with Benjamin and Yorgos, we figured out that we could predict all of these zeta values using a tilted version of the celebrated Weissert, Eden, and Staudacher kernel for the cusp anomalous dimension. So that kernel can be twisted or tilted a little bit, and it gives all these patterns of zetas. Now the question is that a one-off thing for the hexagon, or does it also appear in other amplitudes? And the first thing to do is to collect some perturbative data. And in this case, we understand where the most likely analogous origin is. You're not allowed, due to a Graham determinant constraint, to send all of the cross ratios to 0, but you can send 6 of them to 0, and then the last one goes to 1. And if you look at the NMHV symbol, which Simone Carenhois computed, it's, well, actually at 2 loops. It's also known through 4 loops from the work I mentioned earlier. And that result is consistent with this, but it doesn't tell you any of the zeta values. So you cannot find any input data to understand if there's some pattern to all of the zeta value coefficients if you don't know the zeta values. So one of the motivations for this work was to understand the heptagon functions at function level in order to do that. Also, the 7-point case has a boundary, which is a near collinear limit where 2 of the gluons are getting collinear over here and also over on this side. And in that limit, the Pentagon OPE framework makes predictions. And those predictions actually involve sort of full Pentagon transitions, which depend on the excitations on both sides of this Pentagon. Whereas in the 6-point case, we can test it to high loop orders, but it only looks at simplified Pentagon transitions where there are excitations just on one side. So that's a great thing to explore and test that everything's working fine. And then there's also another limit, the Multi-Regge limit, where for the first time in n=7, you see a particular structure called the central emission block. When you go to, in the 6-point case, you have various structures related to the ends of the ladders that show up in the Multi-Regge limit called impact factors. And of course, you also have something called the BFKL eigenvalue that controls sort of the slopes of trajectories. But at the 7-point case, you can emit something in the middle, turns out, for the first time, this orange blob. And so one can test this conjecture to high orders. But in order to really test it properly, with all the zeta values in place, you need to have the functions. So a 5th motivation is number theoretic. It's related sort of to the question I was asking Johannes. And in the 6-point case, we have a lot of evidence of very intricate behavior under the coaction, where certain things drop out at lower loops or lower weights. And then you can predict that similar things have to drop out at higher weights. And this also has been explored in papers by Oliver Schnetz, Francis Brown, and Eric Panzer in other contexts, spite of the 4 theory and the electron anomalous magnetic moment. And in the setting of the hexagon functions, we find that zeta 2 is not an independent function. It's always attached to logarithms, as I indicated earlier. Also, zeta 3 is not independent. In fact, it sort of is very shy. It doesn't really show up at a certain point in the phase space. So we would like to know what happens for n=7 in order to input this information into part of understanding the structure of this particular setting. So now the outline of the rest of the talk is that I'm going to give you a little refresher course on multiple polylogs and symbols, just the basics. And then I'm going to describe a very important surface that we use in order to supply the necessary zeta values. And that surface interpolates between different limits, and it lets us get around inside this space. It's like a lamppost guiding us inside this 6-dimensional space, whereas this thing is actually 2-dimensional, this CO surface. It interpolates between soft collinear limits and the origins. And we can use it to help fix all the zeta values in the space using various branch cut conditions that all the functions should satisfy. Once we've fixed the values for the whole space, for the whole function space, then we can fix the amplitudes straightforwardly. And then I'll make some plots and make some more sort of number theoretic comments. So multiple polylogs have a long history, and they've been very popular in the past decade or so in describing classes of amplitudes. Now, they are not the whole story for arbitrary amplitudes. There's been a lot of interest in elliptic and beyond elliptic polylogarithmic functions. But for this case, the 7-point case, all we need are multiple polylogs. And they have the property that they're n-fold iterated integrals, which we could define by derivatives if we also specify boundary conditions at a point. And the derivative of the function is a sum of d logs of some symbol letters multiplied by one lower weight functions. And we just put an upper index here to indicate which d log the function goes to. These functions are also referred to as components of a coproduct, or more properly, a coaction, delta, which is associated with a Hopf algebra that maps functions to products of functions. In this case, a function of one lower weight multiplied by a logarithm. And so the derivative is sort of one piece of this coaction. And we can iterate this procedure and differentiate all of these FSKs, weight n-1, and we develop n-2, 1, coproducts, and keep going. And if you keep going all the way down n times, you get the maximally iterated component of the coproduct. When you take a derivative, you start losing information about zeta values. For example, the weight n zeta value, since it's a constant, it would drop out here. You still have some zeta values. By the time you get to the symbol, though, you've lost all zeta values. The arguments of the polylogs play a special role. Those are also called the letters of the symbol. And in these 6- and 7-point amplitudes, we've understood for a while that to manifest the symmetries, it's best to use ratios of 4 brackets of momentum twistors. Once you use these momentum twister variables due to Andrew Hodges and the sort of invariant combinations of them that are determinants of these vectors denoted by 4 brackets, and these carry a scaling that you need to remove to make everything projectively invariant. Those combinations are the right arguments for the polylogs, or more technically, the letters of the symbol. In the 6-point case, the hexagon case, there are 9 of these letters, and 3 of them are cross ratios, which could be rewritten in terms of ratios of Mandelstam variables. 3 more are 1 minus the cross ratios, and then 3 more would be square roots if they're written in terms of U, V, and W. V and W are obtained by cyclic permutations. And these letters were basically laid out in the 2-loop remainder function that was computed, or the results of Del Duca, Dur, and Smirnov were simplified by Goncharov, Spradlin, Virgu, and Volovich when they introduced the symbol of the physics community. And then James and Johannes and I took these letters and we showed you could use them to construct the 3-loop symbol, and so on from there. So at the heptagon level, there are not 3 different variables, U, V, and W, but there are 6 variables. There are 7 UIs, or cross ratios, and they're related to the 4 brackets in a little bit special. Well, here I've introduced the what are called the A letters. So these are the 42 letters of the symbols are shown here. I show 6 of them, and they involve certain cup products that involve intersections of various planes. And then from these 6, you get all 42 by applying 7-fold cyclic permutations of these 6. So instead of having a 9-letter alphabet, you have a 42-letter alphabet. And I mentioned that there are 6 variables. The standard cross ratios that are ratios of just Mandelstam variables are often called UI, and they're ratios of these guys here that simplify a little bit when you take these particular ratios. And there are 7 of them, but they're not all independent. There's a Graham determinant, or a 4th order constraint, that tells you that there are only 6. So the hexagon kinematics is a 3-dimensional space, which we can get around in. And but we want to go to a 6-dimensional space, so we can't really picture that. But in the hexagon case, we have lots of lines where things simplify, where we can move around. And I note that there's a bulk and there's a boundary. The bulk is the interior of the positive octant, where all these are greater than 0, and the boundary is where one or more of these goes to 0. In the hexagon case, we mostly lived in the bulk to do a lot of our manipulations. But the heptagon case requires that we move on to the boundary. And there's an analog to this line here that points between the origin and this point, which we'll rely on. And that analog is what we call the CO surface. In the 7-point case, a 6-dimensional space, it's a 2-dimensional surface that lies inside that space. And what it is it's generic values for 2 of the cross ratios, U3 and U4. 4 others are infinitesimal, and 1 is pinned to 1. And within it, there's some positive region for cluster algebra aficionados. And there are various limits which take you down to 6 point. And the symbol letters on this surface simplify dramatically. Instead of having 42 letters, you have only like 8 letters. And these guys are trivial because they're just correspond to free logarithms. The only non-trivial ones are here. And they're the simplest non-trivial system you can imagine, which is letters U and 1 minus U. And they give you harmonic polylogs with weights 0 and 1, which are about the simplest functions of a generic variable. In fact, this surface is like 2 copies. The functions on this surface are like 2 copies of that U00 line, which some of us know and love from the 6-point case. Now I wanted to mention a little bit about the fact that this CO surface is really one surface, but then there are 7 others where you permute it around. And the interesting thing is, how does the dihedral symmetry act? So there's a D7 symmetry of a heptagon, which allows you to flip over and cycle around. And when you do a flip, one of the flips maintains the surface and just flips it across. So that's very nice. You can see everything manifestly on the surface. The cycle, however, you find that if you cycle by 3, because U7 is 1 and U4 is 1 at this point moves over to here, where U3 is 1 and U4 is infinitesimal. And so you get this nice situation where the CO surfaces are like the petals of this flower. They each touch at one point. So that's a little sort of mnemonic to remind you how things fit together. That touching at points is very important, though, because you can carry constants of integration deduced on one surface to another surface and move things around throughout the surface. Now, where did this surface come from? Well, in brief, it came from a triple scaling limit. There was a parameterization of the endpoint amplitudes by Basso, Sever, and Vieira, which in the 7-point case corresponds to momentum twistors, which have this property. So you can compute all the 4 brackets from this. And if you take the OPE limit that they were originally interested in, that sends the t's to 0, keeping the other guys fixed. But there's also a double scaling limit where you make this transformation. And this CO surface is a triple scaling limit where you scale the t's, the s's, and the f's in exactly this way. And there are very similar limits or analogous limits for n greater than 7 as well, and we're going to be exploiting those to study origins for n greater than 7 as well in future work. So I'm running kind of short of time, so I'm not going to go into much detail about how we implement the branch cut conditions here, but suffice it to say that we do it unlike the 6-point case where we mostly tried to work in the bulk. In this case, we work near the boundary. So in the 6-point case, we are working out here to fix all the zeta values. And in the 7-point case, we kind of have to work on the analog of that line near the origin. So, and that's the CO surface. So there are various conditions that we don't have bad branch cuts, that U3 or U4 equals 1, and so on. And using these conditions, we can fix all the zeta values and fully define the heptagon functions. And there's a fair amount of linear algebra, but most of it was already done at symbol level. And it's fairly light to attach the zeta values because there are fewer functions that have zeta values attached to them. So this CO surface, I showed you the dihedral symmetry acts in an interesting way. But also there are various amplitude conditions like cancellations of spurious poles, which hold on various surfaces where 4 brackets vanish. And those surfaces intersect the CO surfaces at particular lines, like U4 equals 1 or U3 equals 1. And so we can apply these conditions on the CO surface and fix all zeta values attached to the amplitudes in that way, as well as using soft and collinear limits. Now, in fact, for-loop NMHV was a little bit of a surprise in that when you went beyond the symbol level, there were 2 problematic parameters, but we could fix them with a little help from the OPE limit. I'm going to skip through this because things are getting a little short. This is the remainder function on the CO surface, and it was worked out by Golden and Spradlin in the entire space. And when we go onto the surface, we find complete agreement with the Golden-Spradlin expression, which actually collapses to classical polylogs in this limit. And I've written it in a sneaky way so that when you go to the origin, which means you send U3 and U4 to 0, all these terms vanish, and the only thing that survives is this line and its image under a flip. And this has zeta values, and it's only quadratic in logarithms, just like the 6-point origin we had looked at earlier. So there is the same interesting thing happening for the MHV amplitudes in that the remainder function or the logarithm of the amplitude becomes quadratic in the 7-point case. Now, I'm also going to skip through this part. I'm just going to mention that once we have the data on the CO surface, and we have differential relations, which we know in the bulk, we can use them to integrate up off the surface. For example, if we want to compute the amplitude where Golden and Spradlin actually computed it, which was on this line here, the CO surface is not quite good enough. It sets this to 1, which is not quite legal. It turns out it's very close. But we can do the computation on the actual one by a power series expansion around U equals 0. And when we do that, we get exact agreement with Golden and Spradlin. And we fix all the constants of integration at the origin, which is part of the CO surface. And 40 terms are enough. So now I'm going to show you some plots of those functions. And I'm going to plot ratios of successive loop orders. And the reason for doing that is to see how the answer is doing with respect to the expected asymptotic behavior. We know that planar n equals 4 has a finite radius of convergence, and various quantities, if they're well behaved, are likely to behave similarly. And one quantity we know the radius of convergence of is the cusp anomalous dimension. And using that knowledge, we know that asymptotically, the cusp ratio should go to -16, the ratio of L loops to L-1. So that's going to be our sort of target to see how things are doing. When we plot the remainder function, however, we don't see the right thing. We see that the 3-loop ratio to 2 loops is down here. This is the asymptotic cusp value. But then you go to 4/3 and it goes up. We expect it's going to turn over and come down again. We just haven't seen that enough. If instead we plot the logarithm of the MHV amplitude, we see things going in the correct direction. So sometimes you have to pick the right quantity to see what you want to see. When we go to the NMHV case, and now we can show results through 4 loops, the 4-loop result is shown in red here. And we can see that things are flattening as long as we're not too close to boundaries. But the trend of marching towards minus 16, we're still not at quite enough high loop order to see it completely. There's another self-crossing surface, which would look like this in Minkowski region. We're in a Euclidean version of it, but it's a convenient place to plot some things. So here's a couple plots on two lines that go through the surface. And at least when we plot them in such a way that we scale them by their values at this point, then we see that the shapes do not change very much from one loop order to another, which is very similar to the fact that in previous plots, things were becoming flat in the bulk as you go from one loop order to another. And this is very similar to what we saw in the 6-point case. Do I have 2 more minutes?
2 more minutes. Yeah.
Okay, she said grudgingly. So one of the interesting things is how independent are the zeta values? And we did find one surprise, which is that zeta 3 is an independent constant function in the space. And this is surprising because it wasn't independent at 6 points. And you might have expected that that lack of independence would hold by continuity to 7 point, because 6 point is the boundary of 7 point. But in fact, at the 7 point level, you need to introduce zeta 3 as an independent constant. Zeta 2 behaves the same in both cases. It's not independent in both cases. Zeta 4 behaves the same way in both cases. It's independent in both cases. And we don't know what's going on with zeta 5 or zeta 2 times zeta 3. We don't have enough data yet. But it does seem that the very strict coaction behavior in the 6-point case is probably going to be looser or more relaxed in the 7-point case. Now, we do have a little bit of hint of some things interesting with respect to odd zeta values when we are in the parity odd sector. Here I show the sort of data that we do whenever we calculate a bunch of amplitudes. We take all of their derivatives or the number of independent coproducts, and we ask, when do they saturate all of the functions that we have from the bottom up? And do they ever miss saturating for a good reason? And in the parity even sector, we don't see anything interesting happening. Everything seems to saturate. In the parity odd sector, there's one hint here, which maybe it's premature, but this 406 is not the full expected number. We expected 6 more. 406 is the number of symbols. 412 was the expected number of functions, because you can take zeta 3 and multiply it by the 6 weight 3 functions. So these weight 3 functions might be locked to the symbol level weight 6 functions. Of course, if we went to 5 loops and still saw 406, then we would be more sure. And there is one other weird thing in the parity odd sector, which is when we go to the origin and we have parity odd, odd weight, we never get a zeta 2k plus 1 at the origin. But this is another thing where you need more data to be sure about what's going on. And I'll just make a lightning dive to the origin and remark that we have determined from the for-loop MHV results that the log of the MHV amplitude is quadratic in the logarithms. And that is going to supply a lot of input data into understanding the structure of origins at the heptagon level and beyond. But that's for the future. So I'll just conclude by saying we've now bootstrapped every known symbol, previously known symbol, up into a function. We made a lot of use of this CO surface, which has higher point analogs. And we can also, in future work, we'll go into other regions in more detail, including MRK, OPE, and so on, and test some of the proposals that have been made for how amplitudes behave in those limits. So thanks a lot, and sorry for running a little bit over.
No problem. Thank you very much, Lance, for this very interesting talk. Are there questions?
So I have a question. So beyond the coaction principle, can you, there are certain limits when, like the collinear limit, when the 6-point function vanishes and the 7-point goes to 6-point.
Yeah.
In these cases, it needs kind of collaboration between the polylogs and the constants, right? Because you evaluate them, and then there must be cancellation between them, right?
Yeah, well, that was sort of why I thought the zeta 3 was likely to be fixed in the 7-point case, is sort of by continuity. But I think the problem is that the function space is more than just the amplitudes. That is, the amplitudes, if you normalize them the right way, have to behave smoothly. So the remainder function in the 7-point has to go exactly to the remainder function in the 6-point in a softer collinear limit. But then there are these other functions that diverge in this limit. And these divergent functions, the zeta 3 somehow belongs to that sector.
I see. But can you, okay, so even without any details or like a concrete idea, can you think that there are actually kind of a building blocks which contain both the functions and the zeta values, not the full amplitude, just kind of group them into a building blocks with good behavior and kind of combine these things together? So,
well, there are certainly a lot of sectors that have good behavior. Yeah. I mean, you know, buried within this function space are a lot of integrals. And generically, you like to think that the most complicated integrals are typically can be normalized so they're infrared finite. And those integrals typically have this smooth behavior. You know, so you have analogs of these integrals we called omega, like these pentaladder integrals. Right. Of course, you can, you know, put masses on them, and then those things will all have smooth behavior. Okay. But then there's the stuff that doesn't have smooth behavior. There are also divergent integrals in the full Dim-Reg answer, which we remove, but there's some kind of, you know, residue of them with bad collinear or soft behavior. And the different behavior of the zeta values seems to be tied up to those guys.
Okay, but you would generally agree that might be something good in grouping the functions back to the kind of integrals, despite you don't use them in the first place.
Yeah, if we understood more of the integrals, but you know, once we go to 3 loops, we need non-ladder integrals like honeycomb things, and they're very complicated. Yeah. So we don't. Yeah. If we know what they are, we can locate them. In fact, I didn't mention it, but we've located integrals that people have identified, like James and Company and Jake and Company have worked out various 7-point integrals, and we can you know, promote them. Some of them were known at the function level already. We can work them out and identify them in the space, including the zeta values.
Mm-hmm. Okay, thank you.
Are there more questions? I don't see any, so let's thank Lance again.